Adrian, this is James, and I'll be explaining the circuit, our circuit.
And I'm Brian Solaris, and I'll be explaining the block diagram on LabVIEW.
So, this is our circuit, and we have actually two transistors used as a temperature sensor. And this one right here is used for ambient temperature, and this one right here is for the heating. And this is actually powered by the MyRio right here, and it's inputting 5 volts to the rail. As I was saying, the resistor right here is used for heating the transistor, and there's a third NPN transistor right here, which is used as a switch. And the MyRio is inputting a PWM signal. So the PWM signal is going to be controlling how strong the heating signal is. And so we designed it where when the temperature of the transistor changes, the resistance lowers, and because of that, the voltage will also decrease. And going to Brian's part.
Over here, I'll be explaining how the ambient and heater transistors are being measured by MyRio as analog voltages. These voltages are being compared, and we're having the percent difference being output over here. And pulse width modulation will be put out as an analog signal, and that signal will trigger the heater to the duty cycle that we designate over here. It can be set from 0 to 1, 0 being like off and 1 being full power. And we do have a small bias over here, but so you can see the difference is very small, so we can almost neglect it. We set the duty cycle to 0.75. The voltages start to change over here. The duty cycle is at full power when it's at 1 over here, meaning that the resistor will be exposed to 5 volts and heat up faster compared to if you were to set it at 0.5. Duty cycle in the transistor will only be exposed to 2.5 volts. So at full 1 right here, it'll be exposed to the maximum amount of voltage it can receive and heat up faster. Okay, and it's been about a minute after we started running at a duty cycle of 1, and we received a difference of about 0.15 millivolts, which is very significant when it comes to the difference in degrees. So it did warm up and did turn out to be a success. 15 millivolts, excuse me.
So this is our circuit. So what it's doing is that it's taking these two transistors here, ambient and heater, and it's comparing them through this op amp right here. And what it's doing is comparing it to the ambient temperature to make sure that the heater is the same. So it's coming through here, it's going to be multiplied by 1,000 to get the difference in millivolts. And when it does this, we have a graph here that shows the percent difference between the heater and the ambient. Our duty cycle is at 1, which is pretty much 100%. So we have 5 volts going to the rail. So when this activates and lets the PWM go through, we should get a resistor supply of 5 volts, and it should heat up pretty quick.
All right, hey Adrian, I'm Tim. So one of the things we did is because the transistors aren't always equal, we had a bias. So basically this bias would change the voltage reading, the analog voltage reading, so that we could get them 0 when they started. So in this case, we used an if, basically a case structure. So if it reads the tolerance, and if it reads it to be above the tolerance, then it's true, and the duty cycle ends up being whatever the user sets it at, in this case 1. In this case, if the tolerance is lower than, or if this difference is lower than the tolerance, then the duty cycle ends up being 0, so off. As you can see, in this case, we're going to take a lighter to the ambient. So right now, the difference is about 0. It's a little bit under 0, but if we put the lighter on it, you can see here that we get a percent difference, and then also, yeah. So we get a percent difference, and then the resistor or the PWM turns on. You can see it down here as a probe watch. So in this case, it's true, and then it supplies a voltage.